Hi, welcome back. So this is chapter 7, in particular 7.1. We're going to begin with systems of linear equations. And the first section we're going to look at, oops, I already wrote out the section above there. Okay, so first we're going to look at solutions of these things. And okay, so solutions. And look at number 2 from the book. So what does a system of equations look like? Well, here is a system. 9x plus 7y equals 8, and 8x minus 9y equals negative 69. So basically you have two equations, and you're trying to find where they have commonalities to them. Okay. We'll learn in this section, or revisit, if you've already learned this, how to solve these things and find the solutions. And the beginning problems, what they do is hand you the solution, or a potential solution rather, and you have to verify that it is or is not a solution. So the solutions are no longer just x equals something. Now we'll have an ordered pair. So for example, the point 3 comma negative 3 comma 5 is, we're asking, is that a solution to the system? Okay, so how do I determine that? And the way you're going to do it is to substitute. Okay, so first you're going to plug that point into the first equation, the 9x plus 7y equals 8. Okay, so I'll have 9, and this is my x, this is my y. Okay, so 9 times x is negative 3, plus 7 times y, which is 5, equals 8. So I have negative 27 plus 35 equals 8. And of course that's 8 equals 8. So that one works. We have a true statement. We need to have a true statement in both equations. Okay, so I did this one first. Now I'm going to do this equation. Okay, so I'll have 8 times negative 3 minus 9 times 5 equals negative 69. This is negative 24 minus 45 equals negative 69. Negative 69 equals negative 69. That's true. So this thing is a solution. If you get two trues out of it, it is a solution. If you get one true, one false, it is not a solution. If you get two falses, it is not a solution. Okay? The only way for it to be a solution is for it to work in both equations. Okay, so how then may we get these solutions? We'll give you two methods. The first method is the substitution method. Okay, so problem 8, we're given our system 2x minus 3y equals negative 13, and then y equals 2x plus 7. Okay, so what I do first is to get one of the equations solved for one of the variables, and in this case we already have that. We have the second equation is solved for y. In other words, it has y all alone on one side of the equation. Okay. Then I'm going to take that thing and plop it into the unused equation. If you plop it back into itself, you'll end up with a true statement, which just means the equations are the same. Okay, so okay, we take this thing, we're going to plop it into the other equation. So I'll have 2x minus 3 times y, which is 2x plus 7, equals negative 13. So I'll have 2x, I'm going to distribute here. Minus, I'm solving this for x. Minus 6x minus 21 equals negative 13. Combine like terms, so I have negative 4x minus 21 is negative 13. Move the 21 over. It's negative 4x equals, I guess, 8. And x equals negative 2. Okay, so now I need the other answer, basically, the other coordinate. So I have the x part. You remember in the first example we saw the solution is an ordered pair. So we have one part of our solution, we just need the y part. So you could go back to either equation and plug in x. Generally, I believe it's easier to just go back to your first step and use that equation, okay? Because it's already solved for y. So usually in step 3, and you don't have to number your steps or anything. So I'll have y equals 2 times negative 2 plus 7, which is negative 4 plus 7, which is 3. And so our solution will be negative 2 comma 3. Okay. Okay, let's look at some other variations on this problem. So let's try number 14. 2x plus 5y equals 1. And then negative x plus 6y is 8. Okay. So step 1, I want to solve one of the equations for one of the unknowns. And the art of doing this is to avoid fractions. You do not want to introduce more complexity into your world. Okay, so avoid fractions. That's why I chose that second equation, because I know I can solve that for x fairly easily, right? So I just add x to the other side, and then you get 6y minus 8. Then I can take that character and plug them into the unused equation. Okay. So I'll have 2 times x, which is now 6y minus 8, plus 5y equals 1. And I want to solve that for y. Okay, so distribute. y plus 5y is 17y. And it looks like we're getting y as 1. Okay, and then lastly, I'm going to back sub. Again, you could use either of your original equations, or do what I do, and that's basically just borrow this expression from our first step. And you get x equals 6 times 1 minus 8, which is 6 minus 8, which is negative 2. Okay, so our solution this time, negative 2, 1. I'm not sure. In my math lab, they might actually have you put these in curly brackets. So it's a set of ordered pairs. In this case, we just have one ordered pair. So you can have other types of solutions. You can have like infinite solutions and no solutions. We'll talk about that later. So anyways, let's look at another 18. So we have y equals negative 1/2 x plus 2, and y equals 3/4 x plus 7. Okay, both of these equations are solved for y, so you could pick either one. And then substitute that into the unused equation. And essentially what you're doing is setting the equations equal to each other, right? Which is a tried and true technique for solving equations. Solving systems of equations, so finding the intersection points. Just set the equations equal to each other. I hate fractions so much, I'm going to multiply this thing by 4 on both sides. Okay. I'll get negative 2x plus 8 is 3x plus 28. Add 3x or add 2x to both sides, you get 5x. Subtract 28 from both sides, you get negative 20. And then x will be negative 4. Go back to back sub, so I'll just use the first equation. So y equals negative 1/2 times negative 4 plus 2. Negative 1/2 times negative 4 is positive 2 plus 2, and then we'll equal 4. Okay, so at the end, you get negative 4, 4 as your solution. If you want to put it in the curly brackets, that's fine. Okay, so that's our first method, substitution method. Tried and true, it'll work, it will get the job done. Another method you could use is the addition method. And in general, when they're not telling you which method to use, you want to ideally use the quickest one. Okay. Odds are, though, you'll just use the one that you like the most, whichever one that is. 2x minus 7y is 2, and 3x plus y is negative 20. But I really want you to learn both methods, because the substitution method is probably what I use the most, but the addition method is kind of an introduction. It can be used as an introduction to a topic we do later with matrices. Okay. So, anyways, the addition method, what you're doing is hoping for a cancellation if you were just adding column-wise. So if you added 2x plus 3x, you get 5x. If you add negative 7y plus y, you get negative 6y. You're hoping one of the variables cancels out. Okay. And if they don't, what you're going to do is force a cancellation by multiplying one or both equations by a non-zero constant. Okay, so I'm going to multiply the bottom equation by 7. And I write times 7 below the arrow to remind myself what I did. So if I need to go back, I can check my work. Okay, so what do I have? I didn't change the original equation. The second equation, I multiply everything by 7. So we get 21x, 7y equals negative 140. Okay. Now I'll have a cancellation if I add column-wise. So 2x plus 21x is 23x. 7y negative plus positive 7y is 0. On the other side, I'll have negative 138. Divide both sides by 23. And this one turns out to be negative 6. Okay. Now for the back sub, you can use any equation that has both unknowns. I just pick the first one I see, the 2x minus 7y thing. So I have 2 times negative 6 minus 7y equals 2. So negative 12 minus 7y is 2. So I'll have negative 7y equals 14. So I'll have y is negative 2. Our solution, negative 6, negative 2, and we are good to go. Okay, let's try another one. Other variations on this idea. 5x is 6y plus 40, and then 2y is 8 minus 3x. Okay. So the first thing I'm going to do is rewrite it so it's in this sort of ax plus b at y equals c form. So in the first equation, I'm going to subtract 6y on both sides. So I'll have 5x minus 6y equals 40. On the second equation, I'm going to add 3x to both sides. And the reason, I guess, is to get the variables to all line up, and it's less likely you'll make mistakes. Okay, so we have that. Now I'm going to multiply, I guess, the second equation by negative 3. That'll cause a cancellation of the y variables. So I'll have 5x minus 6y equals 40, and then negative 9x minus 6y, and I want positive 3, right? So I apologize, that's not going to work. Okay, so it's going to end up being then, if you multiply everything by positive 3, 9x plus 6y equals 24. And then you'll have the y's cancel. Okay, so 5x plus 9x is 14x. On the other side, you get 64. Divide both sides by 14, and it looks like you're going to have 64 14ths, which is 32 sevenths. Okay. Then we need to plug that back into the equation. I'll use the 2y equals 8 minus 3x. So 2y equals 8 minus 3 times 30 sevenths. So 2y equals, I'm going to need a common denominator here. So on the first term, 8 is the same as 8 over 1. Then I'm going to multiply top and bottom by 7. Okay, so 8 times 7 is 56 over 7 minus, if you multiply 3 over 1 times 32 over 7, you're going to get 96 over 7. 96 minus 56, of course, is 40. So I have 2y equals negative 40 over 7. I'm going to multiply both sides by 1/2. And get y equals negative 20 sevenths. This 2 goes into 40 20 times. So I get 20 over 7 negative. Okay, so the solution here, 32 sevenths, negative 20 sevenths. Make sure you get them in order. X first, then Y second. Okay, I guess unusual solution sets will happen. So these are the infinite or the no solution cases. So section 3, unusual solutions. Okay, and the visual picture, if you've not seen this before, the above problems, if you could plot basically each equation. Each equation is just the equation of a line. Okay, so in the above pictures, what you're dealing with is basically just finding the intersection of two lines, okay, and that would be your solution. So this would be a one solution case. All right, the other solutions come from when either you have parallel lines or the lines are right on top of each other. Okay, so if the lines are parallel, that will be the no solutions case because the lines never touch each other, there's nothing in common, no solutions. Okay. The other case then is when the lines are directly on top of each other. I'm drawing everything in white. Okay. And in that case, the picture basically just looks like there's one line, right? Because they're on top of each other. It looks like one line. And in that case, they intersect each other everywhere. So they'll say there's infinite solutions. Okay. In the no solution case, you'll go through your problem, and what will end up is you'll end up with a false statement resulting. Okay. The mechanics, the algebraic mechanics results. So the algebra, I'll just write the algebra. Algebra results in a false statement. For example, like 0 equals 3. Okay? And then for the infinite solution case, the algebra results in a true statement. For example, 3 equals 3, or 0 equals 0. Okay, so we want to go through and look at an example of each type. So 32, and we have 6x plus 2y equals 7, and then y equals 2 minus 3x. Okay. It's sort of set up like a substitution problem, so that's what I'm going to do. So I pick off the equation that's already solved for one of the unknowns. Then you substitute that into the unused equation. Okay, so second, 6x plus 2 times this 2 minus 3x, 7. Then we solve that for x. So 6x plus 4 minus 6x, I have to distribute, 7. 6x minus 6x, 4 is 7. And there it is. So we ended up with a false statement, and that tells us there are no solutions. If you're using the set notation for your solutions, you can just write the curly brackets. And that's also equivalent to this 0 with the line through it, which they all represent what's called the null set, the set with nothing in it. Okay, let's look at the true solution case, 38. We have 4x minus 2y equals 2, and then 2x minus y equals 1. Okay, I think it's set up properly for an addition method, so I'm going to multiply the second equation by -2. Hope that works. Okay, so we got 4x minus 2y equals 2. Negative 4x plus 2y equals -2. If you add column-wise, you'll have 0 on the left and 0 on the right. So that means there are infinite solutions. So you write infinite solutions. Technically, it's not every solution in the universe, right? It's there's going to be points that don't work. There's going to be points that aren't on this line. So in the homework problems, you'll see them write it more specifically using set notation. Basically, it'll be the set of all coordinates x comma y that lie on the line. So you could pick either equation from where you started. Let's just pick 2x minus y equals 1. Okay. And what that says is this: the solution set is a set of all coordinates x comma y such that 2x minus y equals 1. And that just basically means it's all of the coordinates on that one line. Okay. So if you're the graph both of these, all you would get is one line. They're the same line. Okay. Some applications. In particular, I'll focus on motion applications in this video. So part A, motion. Do I do anything else? No, this is the only one I do. Okay, so for motion problems, the equation is distance equals rate times time. But you can also solve this equation for the other unknowns, right? So you could solve it for r. So r, if you divide both sides by t, you'll get d over t. And then if you solve it for t, you'll get d over r. Okay, so I'm going to look at problem number 62, and I'm going to need to open my book and take a look. So it's about an airplane. It flies somewhere with the wind, and then it flies in the other direction against the wind. So let me find it. This is 7.1. Looking at problem number 62. So 62, when a plane flies with the wind, it can travel 4,200 miles in 6 hours. When the plane flies in the opposite direction against the wind, it can take 7 hours to fly the same distance. Find the average velocity of the plane in still air and the average velocity of the wind. Okay? So it wants, you kind of read the last sentence and it tells you what you're after. So it wants the speed of the plane in still air, so basically just the speed of the plane. And then it's going to want the speed of the wind. So you could use your D equals RT formula to figure this out, or RT equals D. And the first sentence says the boat's crew rowed 18 kilometers downstream with the current in 2 hours. Okay, so it's going to be the rate, okay, and the rate when you're going, oh, sorry, I just read the boat question. Okay, so again, it's 62, sorry. When a plane flies with the wind, it could travel 4,200 miles in 6 hours. When it flies in the opposite direction against the wind, it takes 7 hours to fly in the same direction. Okay, so when a plane flies with the wind, the rate is going to be x plus y. Okay, so it's the rate of the plane, and then the wind is pushing against it, making it go faster. So x plus y will be your rate. Okay. And then it's giving you a time and a distance. Right? So it gives you these other two unknowns. So the time is going to be 6 hours, and the distance is going to be 4,200 miles. Okay, so that's one equation. The other equation is from the second sentence. When the plane flies in the opposite direction against the wind, in other words, its rate will be the speed of the plane, and then the speed of the wind will subtract away. It takes 7 hours to fly the same distance. So rate, x minus y, times the time is 7 hours, and that'll equal the same distance. Okay, so these are our equations. We want to clean them up a little bit. So you could basically divide both sides by 6. Of the first equation, you'll have x plus y equals 700. And the second equation, divide both sides by 7. Okay, so you'll have x minus y equals 600. And then it's just set up for the addition method. So you'll have 2x equals 1300. And then solve that for x. So the speed of the plane in still air will be 650 miles per hour. We still need the speed of the wind, so you go back to either equation. I'll just pick that one. X. So any equation that has both variables will work. So I'm going to plug in 650 plus y equals 700. So y will equal 50. So the speed of the plane will be 650 miles per hour. And then the speed of the wind will be 50 miles per hour. Okay. Okay. In your previous classes, you may have kind of approached it with a chart. If you want to do that, that's fine as well. So with wind versus against wind. And how did the chart thing go? It was like you had rate, time, and then distance. Okay, so the rate with the wind, when you're going with the wind, will be x plus y, against the wind, x minus y. And then it took 6 hours to go with the wind, 4,200 miles. And then 7 hours against the wind to go 4,200 miles. And then you could use those. It's like x plus y times 6 equals 4,200. So you just go straight across and make your equations. X minus y times 7 equals 4,200. And you get the same, system as what we got, just kind of faking our way through the problem. So either method you want to use, if you want to use a chart, that's fine. Okay, that will do it for 7.1. I'm hoping a lot of that was review. If not, you've seen it here first. Hopefully you'll be able to get through the questions, okay? Okay, so thank you for watching, and we'll see you next time.